There is a deceptively simple question that, once examined carefully, reveals layer upon layer of physical reality most people never consider in their daily lives. The question is, how fast are you moving right now? The immediate intuitive answer for most people is that they are sitting still, perhaps in a chair, perhaps lying on a couch, and their speed is zero. But this answer, while perfectly valid in the context of everyday life, is only true relative to the surface of the Earth beneath them. The moment one begins to account for the fact that the Earth itself is doing several things simultaneously, all of which involve motion through space, the answer to the question becomes enormously more complicated, and the numbers involved become staggering. What makes this topic genuinely interesting from a scientific standpoint is not merely the size of the numbers, but the fact that the concept of speed itself turns out to be far less straightforward than it appears. And the history of how humanity came to understand each successive layer of cosmic motion is a story that spans millennia of observation, theory, technological development, and conceptual revolution. To begin with the most immediately tangible form of motion, consider the rotation of the Earth. The Earth completes one full rotation on its axis approximately every 23 hours and 56 minutes, a period known as a sidereal day, which differs slightly from the 24-hour solar day because the Earth is also orbiting the Sun, meaning it must rotate a little extra each day to bring the Sun back to the same apparent position in the sky. The speed at which any given point on the Earth's surface moves due to this rotation depends entirely on latitude. At the equator, the circumference of the Earth is roughly 40,075 kilometers, and dividing that by the length of a sidereal day gives a surface speed of approximately 1,670 kilometers per hour, or about 465 meters per second. This is a substantial speed, considerably faster than the speed of sound in air at sea level, which is roughly 343 meters per second. A person standing on the equator is, in a very real physical sense, moving supersonically relative to the axis of the Earth, though of course this motion is not felt because everything in their immediate environment, the atmosphere, the ground, the buildings, is moving at the same speed and in the same direction. As one moves away from the equator toward either pole, the effective radius of rotation decreases, and so does the surface speed. At a latitude of 45 degrees, the speed is reduced by a factor equal to the cosine of that angle, which is approximately 0.707, yielding a speed of roughly 1,180 kilometers per hour. At the poles themselves, the rotational speed drops essentially to zero, since a person standing directly on the North or South Pole is simply turning in place, rotating around the Earth's axis without translating through space at all, aside from whatever slight wobble might exist due to the precession of the poles. This variation in rotational speed with latitude has real physical consequences. It is the underlying reason why rockets are preferentially launched from sites as close to the equator as possible, since a launch from the equator in the direction of Earth's rotation gives the rocket a free boost of nearly half a kilometer per second, which is a significant fraction of the velocity needed to reach orbit. The European Space Agency's launch site in Kourou, French Guiana, located at about 5 degrees north latitude, was chosen in part for this reason, as was the location of the Kennedy Space Center in Florida at roughly 28 degrees north, which, while not equatorial, is the closest point to the equator on the continental United States, with a coastline facing east over open ocean, allowing spent rocket stages to fall harmlessly into the Atlantic. The recognition that the Earth rotates was itself a hard-won intellectual achievement. While the ancient Greek philosopher Aristarchus of Samos proposed a heliocentric model as early as the 3rd century before the Common Era, and certain Indian astronomers such as Aryabhata in the 5th century of the Common Era explicitly stated that the Earth rotates on its axis, these ideas were not widely accepted in the Western intellectual tradition for many centuries. The dominant cosmological model in European thought from antiquity through the late medieval period was the geocentric system formalized by Claudius Ptolemy in the 2nd century, in which the Earth was stationary and all celestial bodies revolved around it. This model was not simply a matter of ignorance or dogma, it was supported by what appeared to be compelling observational evidence. If the Earth were rotating, critics reasoned, then objects thrown straight upward should land to the west of their starting point, since the ground would have moved beneath them during their flight. Birds in the air should be left behind as the Earth spun beneath them. The atmosphere itself should create a perpetual wind from east to west. None of these effects were observed, and so the stationary Earth seemed like the only reasonable conclusion. It was not until the work of Nicholas Copernicus in the 16th century, published in his De Revolutionibus Orbium Coelestium in 1543, that the heliocentric model was reintroduced into European scientific discourse in a mathematically detailed form. Even Copernicus, however, did not fully resolve the objections about why the effects of Earth's rotation were not felt. That required the development of the concept of inertia, which was articulated in increasingly clear forms by Galileo Galilei in the early 17th century, and later refined by Isaac Newton. Galileo's famous thought experiment about a ship moving at constant velocity, in which a person below decks could not tell whether the ship was moving or stationary by performing any mechanical experiment, was a crucial step in understanding why the rotation of the Earth is imperceptible to its inhabitants. The atmosphere, the oceans, and every object on the surface all share in the Earth's rotation, and since speed is only meaningful relative to something else, there is no way to detect absolute rotational motion from within the rotating frame except through very subtle effects, such as the Coriolis force, which was not formally described until Gaspar Gustave de Coriolis published his analysis in 1835. The Coriolis effect, which causes moving objects on a rotating body to be deflected to the right in the northern hemisphere and to the left in the southern hemisphere, is in fact one of the few directly observable consequences of Earth's rotation in everyday phenomena, though its effects are significant only for motions occurring over large distances or long timescales. It is responsible for the characteristic counterclockwise rotation of large-scale weather systems such as hurricanes in the northern hemisphere and their clockwise rotation in the southern hemisphere. It does not, contrary to popular belief, determine the direction in which water spirals down a drain. At the scale of a household sink or bathtub, the Coriolis force is many orders of magnitude too weak to overcome the effects of the basin's shape, residual currents in the water, and other local factors. Another dramatic demonstration of Earth's rotation came in 1851 when Léon Foucault suspended a large pendulum from the dome of the Pantheon in Paris and showed that the plane of its swing appeared to rotate over the course of the day, a phenomenon that could only be explained if the floor beneath the pendulum was itself rotating. Moving beyond the rotation of the Earth, the next layer of motion is the Earth's orbit around the Sun. The Earth travels in a slightly elliptical path around the Sun with an average distance of approximately 149.6 million kilometers, a distance defined as 1 astronomical unit. The orbital period is 1 sidereal year, approximately 365.256 days, and the orbital circumference is roughly 940 million kilometers. Dividing the circumference by the period gives an average orbital speed of about 107,280 kilometers per hour, or approximately 29.8 kilometers per second. This is a remarkable speed, more than 64 times faster than the rotational speed at the equator, and it means that in the time it takes to read a single sentence, the Earth has moved roughly several hundred kilometers along its orbital path. Because the orbit is elliptical rather than perfectly circular, the Earth's orbital speed varies slightly over the course of the year, moving faster when it is closer to the Sun, a point called perihelion, which currently occurs around January 3rd, and slower when it is farther from the Sun, at aphelion, around July 4th. The difference is not large. The speed at perihelion is about 30.3 kilometers per second, while at aphelion it drops to about 29.3 kilometers per second, a variation of about 3%. This behavior was first described empirically by Johannes Kepler in his second law of planetary motion, published in 1609, which states that a line segment connecting a planet to the Sun sweeps out equal areas in equal intervals of time. The physical explanation for this law came later, with Newton's formulation of the law of universal gravitation in 1687, which showed that the varying speed was a natural consequence of the conservation of angular momentum in an inverse square gravitational field. The discovery that the Earth moves around the Sun, rather than the other way around, was one of the most consequential intellectual developments in human history, and the resistance it encountered was not merely a matter of religious or institutional conservatism, though those factors were certainly involved. The heliocentric model faced genuine empirical challenges that took centuries to resolve. One of the most important was the apparent absence of stellar parallax, the tiny shift in the apparent positions of nearby stars against more distant background stars that should be observable if the Earth is truly moving across a baseline of 2 astronomical units, the diameter of its orbit, over the course of 6 months. Copernicus was aware of this objection and responded by proposing that the stars were simply so far away that the parallax was too small to detect with existing instruments, which turned out to be correct, but was not confirmed observationally until 1838, when Friedrich Wilhelm Bessel measured the parallax of the star 61 Cygni and found it to be about 0.314 arc-seconds, corresponding to a distance of approximately 10.3 light-years. The mere fact that nearly 3 centuries elapsed between the proposal of the heliocentric model and the first direct detection of stellar parallax gives some sense of just how precise astronomical measurements needed to become before this particular prediction could be tested. The angles involved are extraordinarily small. Even the closest star system to the Sun, Alpha Centauri, has a parallax of only about 0.76 arc-seconds, which is roughly the angle subtended by a coin viewed from a distance of several kilometers. The Earth's orbital velocity of roughly 30 kilometers per second has a number of interesting physical consequences. One is the phenomenon of stellar aberration, first observed by James Bradley in 1727. Bradley noticed that the apparent positions of stars shifted by a small amount, about 20.5 arc-seconds, over the course of a year, in a pattern that was different from what would be expected from parallax. The direction of the shift was always related to the direction of the Earth's orbital motion at that time of year, not to the star's distance. Bradley correctly interpreted this as an effect analogous to the way raindrops, falling vertically in still air, appear to come from a direction ahead of a moving person, requiring the person to tilt their umbrella forward. In the same way, the finite speed of light combined with the Earth's motion means that a telescope must be tilted very slightly in the direction of motion to catch the incoming light of a star. The magnitude of the aberration is determined by the ratio of the Earth's orbital speed to the speed of light, which is approximately 1 part in 10,000, and Bradley's measurement of this ratio provided an independent estimate of the speed of light that was consistent with the earlier measurement by Ole-Römer, using the timing of eclipses of Jupiter's moon Io. Now, the combination of Earth's rotational speed and its orbital speed already places any observer on the Earth's surface in a state of complex motion, but these two motions are far from the whole story. The Sun itself is not stationary. It is one of several 100 billion stars in the Milky Way galaxy, and it is orbiting the center of that galaxy at a considerable speed. Determining the Sun's motion within the galaxy requires knowing 2 things: the distance of the Sun from the galactic center and the time it takes to complete one orbit. Modern measurements place the Sun at a distance of approximately 26,000 light-years from the center of the Milky Way, although this figure has been revised significantly over the past century as observational techniques have improved. In the early 20th century, the Dutch astronomer Jacobus Kapteyn estimated the size of the Milky Way and the Sun's position within it based on star counts, and his model placed the Sun relatively close to the center of a much smaller galaxy. This was largely because interstellar dust absorbs and scatters visible light, making the galaxy appear smaller and more symmetric than it actually is. Harlow Shapley, working in the 1910s and 1920s, used the distribution of globular clusters to argue that the galactic center was much farther away than Kapteyn had estimated, and that the Sun was located in the outskirts of the galaxy rather than near its center. Shapley's estimate of the distance was too large, roughly 50,000 light-years. But the qualitative conclusion that the Sun is far from the galactic center was correct, and represented a major shift in understanding. The orbital speed of the Sun around the galactic center has been measured through a combination of techniques, including observations of the radial velocities of other stars, the proper motions of distant radio sources, and the dynamics of the galactic disk. The current best estimate is approximately 220 to 230 kilometers per second, often cited as roughly 228 kilometers per second, though the precise value depends on the measurement method and the assumptions made about the galaxy's mass distribution. At this speed, the Sun takes approximately 225 to 250 million years to complete one orbit around the galactic center, a period sometimes called a galactic year or a cosmic year. Since the Sun is approximately 4.6 billion years old, it has completed roughly 18 to 20 full orbits since its formation. This orbital speed is vastly greater than either the Earth's rotational speed or its orbital speed around the Sun. At 228 kilometers per second, the entire solar system is hurtling through the galaxy at approximately 820,000 kilometers per hour. To put this in perspective, the fastest human-made object as of the early 21st century is the Parker Solar Probe, which at its closest approaches to the Sun reaches speeds of about 190 kilometers per second, still slower than the speed at which the Sun orbits the galaxy. The solar system's motion around the galaxy carries with it all the planets, moons, asteroids, comets, and other bodies gravitationally bound to the Sun, and none of this motion is detectable from within the solar system by any mechanical means, for the same reason that the Earth's rotation is imperceptible. Everything in the local environment is moving together, and only measurements made relative to external reference points, such as distant stars, pulsars, or extragalactic sources, can reveal the motion. The direction of the Sun's galactic orbit is approximately toward a point in the sky, near the constellation Cygnus, although the Sun's motion is not purely circular. Like most stars in the galactic disk, the Sun also oscillates vertically above and below the midplane of the galaxy, with a period of roughly 64 to 70 million years and an amplitude of perhaps 200 to 300 light-years above or below the midplane. Some researchers have attempted to correlate this oscillation with periodic mass extinction events in the geological record, hypothesizing that passages through the denser central plane of the galaxy might increase the flux of cosmic rays or disturb the Oort cloud of comets, leading to impacts on Earth, but the evidence for such correlations remains disputed and is not considered well established. Additionally, the Sun has a small component of radial motion, moving slightly inward or outward relative to the galactic center over time. This means the Sun's orbit is not a closed ellipse, but a more complex rosette-like pattern, which is a common feature of orbits in a non-point mass gravitational potential like that of a galaxy, where the mass is distributed over a large volume rather than concentrated at a single central point. Understanding the Sun's velocity within the galaxy required not only the development of spectroscopy, which allowed the measurement of stellar radial velocities through the Doppler shift of spectral lines, but also the recognition that the Sun's motion could be disentangled from the overall pattern of stellar motions in the solar neighborhood. William Herschel, as early as 1783, analyzed the proper motions of 13 stars and concluded that the Sun appeared to be moving toward a point in the constellation Hercules, which he called the solar apex. This was a remarkable insight for its time, though his estimate of the solar apex was somewhat different from modern values because of the limited data available and the difficulty of separating the Sun's motion from the random individual motions of other stars. The concept of the local standard of rest was developed in the 20th century as a way to define a reference frame based on the average motion of stars in the solar neighborhood, allowing the Sun's peculiar velocity, its deviation from the mean local circular orbit, to be measured separately from the overall circular rotation of the galactic disk. The Sun's peculiar velocity, relative to the local standard of rest, is approximately 13 to 20 kilometers per second, depending on which stars are used to define the standard, and this motion is directed roughly toward a point slightly above the galactic plane and ahead of the Sun in its orbit. It is worth pausing here to consider how these various velocities combine. The combination is not simply a matter of adding numbers, because the motions are in different directions and the velocities are vectors, not scalars. The Earth's rotational speed at the equator is about 0.465 kilometers per second, directed roughly eastward along the equator. The Earth's orbital speed around the Sun is about 29.8 kilometers per second, directed along the tangent to its orbit at any given moment. The Sun's orbital speed around the galactic center is about 228 kilometers per second. Each of these velocities changes direction continuously as the Earth rotates, as it orbits the Sun, and as the Sun orbits the galaxy. At any given instant, the actual velocity of a person standing on the Earth's surface relative to the galactic center is the vector sum of all these components, and because the orientations of these motions change continuously, the magnitude of the resultant velocity also changes slightly over the course of a day, a year, and a galactic orbit. However, the largest contribution by far is the Sun's galactic orbital velocity, and so the total speed relative to the galactic center is always somewhere in the vicinity of 228 kilometers per second, with relatively small fluctuations due to the other motions. But even the galactic center is not a fixed point in space. The Milky Way galaxy itself is moving, and this introduces yet another layer of velocity that must be accounted for if one wishes to talk about motion relative to anything beyond our own galaxy. The Milky Way is part of a collection of galaxies known as the Local Group, which contains more than 80 known galaxies, though most of them are small dwarf galaxies. The two dominant members are the Milky Way and the Andromeda Galaxy, also known as Messier 31, which is located approximately 2.5 million light-years away. These two galaxies are approaching each other at a speed of approximately 110 kilometers per second, as measured by the blue shift of spectral lines from the Andromeda Galaxy. This approach is primarily the result of the mutual gravitational attraction between the two galaxies, which are massive enough to overcome the general expansion of the universe at their relatively close separation. Current models predict that the Milky Way and the Andromeda Galaxy will undergo their first close encounter in approximately 4 to 5 billion years, eventually merging into a single larger galaxy over the course of several additional billion years. The motion of the Milky Way within the Local Group can be decomposed into several components. There is the motion toward Andromeda just mentioned, but there is also motion relative to the center of mass of the Local Group as a whole, which is located somewhere between the Milky Way and Andromeda, closer to Andromeda because it is likely somewhat more massive. The velocity of the Milky Way relative to the center of mass of the Local Group is estimated at roughly 100 to 300 kilometers per second, depending on the assumptions made about the masses of the various member galaxies and the distribution of dark matter in the group. Beyond the Local Group, we enter the realm of large-scale cosmic motions, and here the numbers become truly enormous. The Local Group is itself part of a larger structure known as the Virgo supercluster, or sometimes the Local Supercluster, a vast collection of galaxy groups and clusters spanning roughly 110 million light-years. The center of mass of this structure is located approximately in the direction of the Virgo cluster, a large cluster of over 1,000 galaxies about 54 million light-years away. The Local Group, along with many other galaxy groups, is falling toward the Virgo cluster at a speed of approximately 300 kilometers per second, though this infall velocity is partially offset by the expansion of the universe, which is carrying the Virgo cluster away from us at the same time. The recognition that the universe is expanding was one of the transformative scientific discoveries of the 20th century. Edwin Hubble's 1929 announcement that distant galaxies appeared to be receding from us at speeds proportional to their distances, based on the redshifts of their spectral lines and distance estimates using Cepheid variable stars as standard candles, established what is now known as Hubble's law. The proportionality constant, the Hubble constant, is currently measured at approximately 67 to 74 kilometers per second per megaparsec, with the precise value being a subject of active debate and investigation due to a persistent discrepancy between measurements based on the local distance ladder and those based on the cosmic microwave background radiation. A megaparsec is approximately 3.26 million light-years, so a Hubble constant of 70 kilometers per second per megaparsec means that for every additional 3.26 million light-years of distance from us, a galaxy is receding approximately 70 kilometers per second faster. For the Virgo cluster, at a distance of about 16.5 megaparsecs, the recession velocity due purely to the expansion of the universe would be roughly 1,150 kilometers per second, while the actual observed recession velocity is somewhat less, around 1,100 kilometers per second, because the gravitational attraction between the Local Group and the Virgo cluster partially counteracts the expansion. In 2014, R. Brent Tully and colleagues published a study that redefined the supercluster concept. based on maps of galaxy velocities and the gravitational basins of attraction that govern them. They identified a much larger structure, which they named Laniakea, a Hawaiian word meaning immense heaven, encompassing the Virgo supercluster and several neighboring superclusters, with a total extent of roughly 520 million light-years and containing roughly 100,000 galaxies, with a total mass of approximately 10 to the 17th solar masses. The boundary of Laniakea is defined not by any visible wall of galaxies, but by the surface at which the flows of galaxies diverge, with galaxies on one side falling toward the center of mass of Laniakea and galaxies on the other side falling toward adjacent attractors. This center of mass, known as the Great Attractor, is located approximately 250 million light-years from us, in the direction of the constellations Centaurus and Norma. The local group, and with it the entire Virgo supercluster, is falling toward the Great Attractor at an estimated speed of approximately 600 to 630 kilometers per second. The Great Attractor was first identified in the late 1970s and early 1980s through analyses of the peculiar velocities of galaxies, that is, the component of their velocities that deviates from what would be expected from a smooth, uniform Hubble expansion. A group of astronomers informally known as the Seven Samurai published a landmark paper in 1988 showing that a large-scale flow of galaxies existed in the direction of Centaurus, implying the presence of a massive concentration of matter in that region. However, the Great Attractor is located behind the zone of avoidance, the region of the sky where the disk of the Milky Way blocks our view of extragalactic objects, with gas, dust, and dense star fields, making direct observation difficult. X-ray surveys and radio observations, which can penetrate the obscuring material, have revealed a large concentration of galaxy clusters in that direction, including the Norma cluster, which appears to be near the center of the mass concentration responsible for the gravitational pull. More recent work has suggested that the Great Attractor alone may not account for the full motion of the local group, and that even larger structures at greater distances may be contributing to the flow. The Shapley supercluster, located approximately 650 million light-years away in the same general direction as the Great Attractor but beyond it, is one of the largest known concentrations of galaxies in the observable universe and is thought to contribute significantly to the gravitational pull experienced by our local region of space. Some researchers have proposed that the combined gravitational influence of the Great Attractor, the Shapley supercluster, and other massive structures, along with the possible influence of underdense voids behind us that effectively push us forward by providing less gravitational pull, accounts for the observed peculiar velocity of the local group. This brings us to what is perhaps the most fundamental and well-defined measure of our motion through space: our velocity relative to the cosmic microwave background radiation, or CMB. The CMB is the remnant radiation from the early universe emitted approximately 380,000 years after the Big Bang, when the universe had cooled enough for protons and electrons to combine into neutral hydrogen atoms, allowing photons to travel freely for the first time. This radiation fills all of space and has been cooled by the expansion of the universe to a current temperature of approximately 2.725 Kelvin. It is, to an extraordinary degree, uniform in all directions, with temperature fluctuations at the level of roughly 1 part in 100,000, which correspond to the tiny density variations in the early universe that eventually grew into the galaxies and large-scale structures we observe today. The CMB provides a natural rest frame for the universe as a whole, or at least for the observable universe. If an observer were at rest with respect to the CMB, they would measure the same temperature in every direction. However, if the observer is moving relative to the CMB, the radiation ahead of them in the direction of motion would be blue-shifted to slightly higher frequencies and therefore slightly higher temperatures, while the radiation behind them would be red-shifted to lower temperatures. This produces a dipole pattern in the CMB temperature map, with one hemisphere of the sky appearing slightly warmer than average and the opposite hemisphere slightly cooler. This dipole was first measured in the 1970s by a series of high-altitude balloon experiments and U-2 aircraft observations, and it was measured with high precision by the COBE satellite in the early 1990s, and later by the WMAP and Planck satellites. The amplitude of the CMB dipole corresponds to a velocity of approximately 370 kilometers per second, directed toward a point in the sky near the constellation Leo. However, this is the velocity of the Sun relative to the CMB. When the Sun's motion around the galactic center is subtracted, the resulting velocity of the Milky Way galaxy as a whole relative to the CMB is approximately 620 kilometers per second, directed toward a point between the constellations Centaurus and Hydra. This is generally consistent with the direction toward the Great Attractor and the Shapley supercluster, supporting the interpretation that the Milky Way's motion relative to the CMB is driven primarily by the gravitational influence of these large-scale structures. It is essential to emphasize that this velocity of 620 kilometers per second relative to the CMB is the closest thing we have to an absolute speed through space, but even this description requires careful qualification. According to the theory of special relativity, formulated by Albert Einstein in 1905, there is no preferred reference frame in the universe, and all inertial frames are equally valid for describing the laws of physics. The CMB rest frame is not more correct than any other frame in a fundamental physical sense. It is simply a particularly natural and convenient frame because it is defined by the most ancient and most uniformly distributed radiation in the universe. A hypothetical observer at rest relative to the CMB would measure no dipole anisotropy, and in that sense they would be at rest with respect to the universe. But this does not mean they are in a state of absolute rest in the Newtonian sense. The concept of absolute rest was abandoned with the failure to detect the luminiferous ether in the Michelson-Morley experiment of 1887 and the subsequent development of special relativity, and it has not been revived by the discovery of the CMB. Even though the CMB does provide a preferred frame in a cosmological, though not a fundamental physical sense, the distinction between these two senses of preferred frame is subtle but important. Special relativity states that the laws of physics are the same in all inertial frames, and no experiment performed entirely within a closed laboratory can determine the laboratory's velocity through space. The CMB rest frame does not violate this principle. It is simply a frame defined by the matter and radiation content of the universe, and the fact that we can determine our motion relative to it is no different in principle from the fact that we can determine our motion relative to the surface of the Earth or the center of the galaxy. The CMB frame is special because of the specific cosmological history that produced it, not because of any fundamental asymmetry in the laws of physics. Now let us attempt to compile all of these velocities into a single picture. A person standing on the equator is moving at about 0.465 kilometers per second due to Earth's rotation. The Earth is moving at about 29.8 kilometers per second in its orbit around the Sun. The Sun is moving at about 228 kilometers per second in its orbit around the center of the Milky Way. The Milky Way is moving at roughly 620 kilometers per second relative to the cosmic microwave background. These numbers cannot simply be added together to give a total speed, because they are vectors pointing in different directions, and the resulting speed depends on how these vectors align at any given moment. When all components are accounted for, the total speed of an observer on Earth relative to the CMB fluctuates around approximately 370 kilometers per second, with the specific value at any moment depending on the time of year, the time of day, and the observer's latitude, since all of these affect the direction and magnitude of the smaller velocity components relative to the dominant galactic and extragalactic motions. The fact that our total speed relative to the CMB is less than the speed of the Milky Way relative to the CMB might seem puzzling at first, but it is explained by the fact that the Sun's orbital motion around the galactic center is, at the present time, partially directed away from the direction of the Milky Way's motion relative to the CMB. If the Sun's galactic orbital velocity happened to be pointed in the same direction as the Milky Way's CMB velocity, the total would be closer to 850 kilometers per second, and if it were pointed in exactly the opposite direction, it would be closer to 400 kilometers per second. The current value of roughly 370 kilometers per second for the Sun's CMB velocity indicates that the Sun's galactic orbital velocity has a significant component opposing the Milky Way's CMB motion, reducing the total when the two are combined vectorially. Converting 620 kilometers per second into more intuitive units, This is approximately 2,232,000 kilometers per hour, or about 0.2% of the speed of light. It means that relative to the CMB, the entire Milky Way, with its hundreds of billions of stars, its trillions of planets, its vast clouds of gas and dust, and its enormous halo of dark matter, is rushing through space at more than 2 million kilometers every hour. In the time it takes to blink, perhaps 300 milliseconds, the galaxy has moved about 186 kilometers relative to the CMB. In a single human heartbeat, it has traveled about 500 to 600 kilometers. In a day, it covers roughly 53 million kilometers, which is more than a third of the distance from the Earth to the Sun. These numbers raise a question that has occupied physicists and philosophers alike. Does this motion have any physical consequences? In everyday life, the answer is essentially no. As noted earlier, the principle of relativity ensures that no local experiment can detect uniform motion through space, and all of the velocities discussed here are, to an extremely good approximation, uniform over the timescales and length scales of human experience. The accelerations involved, even the acceleration due to the Earth's rotation or its orbit around the Sun, are very small compared to the local gravitational acceleration at the Earth's surface, and the curvature of the various orbits is so gentle that they are nearly indistinguishable from straight-line motion over short distances. A person sealed inside a perfectly smooth, vibration-free room with no windows and no access to external information would have no way to determine how fast they were moving relative to the CMB, or relative to anything else for that matter. However, there are contexts in which these motions do have measurable effects. The aberration of starlight mentioned earlier is one. The CMB dipole itself is another. A third example is the time dilation predicted by special relativity, which states that a moving clock runs slower than a stationary one, with the amount of slowing depending on the ratio of the clock's speed to the speed of light. At 620 kilometers per second, the time dilation factor is approximately 1 plus 2.14 times 10 to the negative 6, meaning that a clock at rest relative to the CMB would run about 0.02% faster than a clock on the Earth. This is an incredibly tiny effect, far too small to be noticed in daily life, but it is well within the measurement capabilities of modern atomic clocks, which can achieve fractional frequency stabilities of parts in 10 to the 18th. In practice, the time dilation effects that are most relevant for real-world applications, such as the operation of the global positioning system, are those due to the relative velocities between satellites and receivers on the ground and the gravitational time dilation predicted by general relativity, rather than the much smaller effects due to our cosmic velocity. There is another effect that becomes relevant at cosmological scales, which is the kinematic Sunyaev-Zeldovich effect, sometimes called the KSZ effect. When CMB photons pass through a cluster of galaxies that is moving relative to the CMB rest frame, the electrons in the hot intra-cluster gas scatter some of the photons, and because the cluster has a bulk velocity relative to the CMB, this scattering introduces a small additional spectral distortion that can, in principle, be measured. The KSZ effect has been detected statistically by combining data from surveys of galaxy clusters with CMB maps from the Atacama Cosmology Telescope and the South Pole Telescope, and it provides a way to measure the peculiar velocities of distant galaxy clusters, complementing other methods such as the Tully-Fisher relation and the fundamental plane for elliptical galaxies. The history of velocity measurement in astronomy is, in many ways, a history of ever-increasing precision and ever larger reference frames. The earliest astronomers could only measure the apparent motions of celestial objects against the background of fixed stars, which gave them proper motions in the plane of the sky, but no information about motion along the line of sight. The development of spectroscopy in the 19th century, pioneered by scientists such as Joseph von Fraunhofer, Gustav Kirchhoff, and Robert Bunsen, made it possible to measure radial velocities through the Doppler shift, opening up the third dimension of velocity space. William Huggins made the first measurement of a stellar radial velocity in 1868, finding that the star Sirius was receding from the Sun at about 46 kilometers per second, a value later revised with improved data. Vesto Slipher, working at the Lowell Observatory in the 1910s, measured the radial velocities of dozens of spiral nebulae, finding that most were receding at speeds of hundreds or even thousands of kilometers per second, a discovery that was crucial for Hubble's later formulation of the velocity-distance relation. The measurement of the CMB dipole required an entirely different technological approach. Because the CMB is microwave radiation with a peak wavelength of about 1.9 millimeters, corresponding to a frequency of about 160 gigahertz. Detecting small temperature differences in it requires microwave receivers with exceptional sensitivity and stability, as well as careful removal of foreground contamination from the Milky Way and other sources. The first definitive detection of the CMB dipole was reported in 1977 by George Smoot, Mark Gorenstein, and Richard Muller, based on observations made with a differential microwave radiometer flown on a U-2 aircraft at an altitude of about 20 kilometers, above most of the water vapor in the atmosphere that would otherwise absorb the microwave signal. Their measurement gave a velocity consistent with the current best value, though with much larger uncertainties. The COBE satellite, launched in 1989, measured the dipole with much greater precision, and the WMAP and Planck missions have continued to refine the measurement. It is worth noting that the interpretation of the CMB dipole as being entirely due to our motion relative to the CMB rest frame is an assumption, albeit one that is very well supported by the data. In principle, part of the dipole could be intrinsic, meaning that it could reflect a genuine large-scale temperature difference in the CMB that existed at the time of last scattering, rather than a Doppler effect due to our motion. However, the expected intrinsic dipole from the standard cosmological model, the lambda CDM model, is many orders of magnitude smaller than the observed dipole, and attempts to detect any residual intrinsic dipole after subtracting the kinematic contribution have so far yielded results consistent with zero. There have been some papers in recent years suggesting subtle anomalies in the CMB that might indicate a non-standard cosmology, but these remain controversial and are not part of the mainstream consensus. Another way to approach the question of cosmic velocity is to consider the expansion of the universe itself. According to the current cosmological model, the universe is expanding in the sense that the distances between gravitationally unbound objects are increasing over time. This expansion is described by the scale factor, a function of time that multiplies all distances in the universe. The rate at which the scale factor changes, divided by the scale factor itself, gives the Hubble parameter, which at the present time has the value of the Hubble constant, approximately 67 to 74 kilometers per second per megaparsec. For very distant objects, the recession velocity due to the expansion of the universe can exceed the speed of light. For example, galaxies at a redshift of about 1.5, corresponding to a current distance of roughly 14 billion light-years, are receding from us at approximately the speed of light. Galaxies at higher redshifts are receding faster than light, and the most distant objects visible in the observable universe, at redshifts of about 1100, the surface of last scattering for the CMB, are receding at many times the speed of light. This might seem to violate the principle from special relativity that nothing can travel faster than light, but the resolution is that the cosmological recession velocity is not a velocity in the usual sense of special relativity. Special relativity's speed limit applies to objects moving through space, whereas the cosmological recession is a result of space itself expanding, carrying objects along with it. Two galaxies that are receding from each other at superluminal velocities are not moving through space faster than light. Rather, the space between them is expanding fast enough that their separation increases at a rate greater than the speed of light. This distinction is not merely semantic, it has real physical consequences. For instance, it is possible for light emitted by a galaxy that was receding faster than light at the time of emission to eventually reach us, because the expansion rate can change over time, and the light can gradually make progress toward us as it enters regions of space that are expanding more slowly. The question of whether one can meaningfully assign a single number to how fast we are moving through space thus depends critically on what reference frame is chosen and what kinds of motion are included. If the reference frame is the local surface of the Earth, the answer is 0. If the reference frame is the center of the Earth, the answer depends on latitude and ranges from 0 at the poles to about 465 meters per second at the equator. If the reference frame is the Sun, the answer includes the Earth's orbital velocity and is approximately 30 kilometers per second. If the reference frame is the center of the Milky Way, the answer is dominated by the Sun's galactic orbital velocity and is roughly 230 kilometers per second. If the reference frame is the CMB, the answer for the Sun is approximately 370 kilometers per second, and for the Milky Way as a whole, approximately 620 kilometers per second. And if one considers the cosmological recession of distant objects, the velocity depends on distance and can be made as large as one wishes by looking at objects far enough away. Each of these velocities was discovered through a distinct program of observation and theory, often separated by centuries, and each discovery required not only new instruments but new conceptual frameworks. The recognition that the Earth rotates required the concept of inertia. The recognition that the Earth orbits the Sun required the abandonment of the geocentric model, and, eventually, the detection of stellar parallax and aberration. The recognition that the Sun orbits the galaxy required the development of spectroscopy, statistical methods for analyzing stellar motions, and an accurate understanding of the size and structure of the Milky Way. The recognition that the Milky Way is moving relative to other galaxies required the identification of galaxies as external to our own, the measurement of galactic redshifts, and the construction of distance ladders to calibrate those redshifts. And the measurement of our velocity relative to the CMB required the detection of the CMB itself, which was only accomplished in 1965 by Arno Penzias and Robert Wilson, followed by increasingly sensitive satellite observations over the subsequent decades. The development of accurate distance measurements, which are essential for converting observed angular motions and redshifts into physical velocities, is itself a fascinating story of accumulating uncertainties and systematic errors. The cosmic distance ladder, as it is often called, consists of a series of methods, each calibrated against the one below it. At the base are geometric methods, such as parallax, which are limited to relatively nearby stars. Above that are spectroscopic methods, such as the period luminosity relation for Cepheid variables, discovered by Henrietta Swan Leavitt in 1908, and calibrated using parallax measurements of the nearest Cepheids. Above that are methods based on type Ia supernovae, which are used as standard candles at cosmological distances. Each rung of the ladder introduces its own uncertainties, and errors at lower rungs propagate upward, potentially biasing all subsequent distance and velocity measurements. The persistent discrepancy in the measured value of the Hubble constant, known as the Hubble tension, may be a sign that one or more rungs of the distance ladder have systematic errors, or it may indicate new physics beyond the standard cosmological model. This is one of the most actively debated topics in cosmology as of the early 2020s. The measurement of peculiar velocities, the velocities of galaxies relative to the smooth Hubble flow, has been a particularly challenging area. These velocities are typically small compared to the recession velocities at cosmological distances, meaning that they appear as small deviations from the expected redshift distance relation. Extracting them requires very accurate distance measurements, independent of redshift, to determine how much of a galaxy's redshift is due to the Hubble expansion and how much is due to peculiar motion. The Tully-Fisher relation, which correlates the luminosity of a spiral galaxy with the width of its 21-centimeter hydrogen emission line, and the fundamental plane for elliptical galaxies, which relates size, surface brightness, and velocity dispersion, are two of the primary tools used for this purpose. Large surveys of peculiar velocities, such as the Cosmic Flows project, led by Tully and collaborators, have mapped the velocity field in the local universe out to distances of several 100 million light-years, revealing the complex web of flows toward attractors and away from voids that characterize the large-scale dynamics of the cosmic matter distribution. One of the more striking findings from these surveys is the extent to which the local velocity field is dominated by relatively few, very massive structures. The Great Attractor, the Shapley supercluster, and the Perseus-Pisces supercluster are among the primary attractors identified in the surveys, and the dipole repeller, a large underdense region in the direction opposite to our motion, was identified in 2017 by Yehuda Hoffman and collaborators as contributing to our motion by providing less gravitational pull, effectively pushing us toward the attractors. This concept of gravitational repulsion by voids is not a violation of general relativity or any known physical law. It is simply a consequence of the fact that an underdense region exerts less gravitational attraction than the average, and so an object between an overdense region and an underdense region will experience a net acceleration toward the overdense region. In the frame of the Hubble expansion, this appears as if the void is repelling nearby matter, though the underlying physics is entirely conventional. The observation that our local region of the universe has a substantial peculiar velocity relative to the CMB has implications for precision cosmology. When measuring the CMB, the first step is to subtract the dipole, which is assumed to be entirely kinematic. If even a small fraction of the observed dipole were intrinsic to the CMB, this would affect the inferred cosmological parameters derived from the higher-order temperature fluctuations. The Planck satellite's final data release in 2018 found no significant evidence for an intrinsic dipole, but the question continues to be revisited as measurement precision improves. It is also interesting to consider the velocity of the Milky Way in the context of the virial theorem and the dynamics of the local group. The virial theorem, a result from classical mechanics that relates the average kinetic energy of a gravitationally bound system to its average potential energy, can be used to estimate the total mass of the local group from the relative velocities of its member galaxies. The approach velocity of the Milky Way and Andromeda, combined with their separation and the age of the universe, implies a total local group mass of roughly 3 to 5 times 10 to the 12th solar masses, most of which is in the form of dark matter. This mass estimate is consistent with independent estimates derived from the rotation curves of the individual galaxies, the motions of satellite galaxies, and gravitational lensing measurements. The concept of dark matter itself is deeply connected to the measurement of cosmic velocities. The first strong evidence for dark matter came from Fritz Zwicky's 1933 study of the Coma cluster, in which he measured the velocities of galaxies within the cluster and found that they were moving so fast that the cluster should have flown apart long ago if the only matter present were the visible matter. He concluded that the cluster must contain a large amount of unseen matter, which he called Dunkel Materie. This conclusion was strengthened by Vera Rubin and Kent Ford's work in the 1970s on the rotation curves of spiral galaxies, which showed that stars in the outer regions of galaxies were orbiting at speeds much higher than expected based on the visible mass, implying the presence of massive halos of dark matter extending far beyond the visible disk. The Sun's own orbital velocity of approximately 228 kilometers per second is, in fact, significantly higher than what would be expected if the Milky Way contained only the visible baryonic matter. Models of the Milky Way's rotation curve indicate that the dark matter halo contributes the majority of the gravitational potential at the Sun's distance from the galactic center, and the Sun's orbital speed is one of the key observational constraints used in fitting models of the Milky Way's mass distribution. Returning to the question of how these velocities are experienced, or rather not experienced, there is a deeper point about the nature of motion in physics that is worth examining. In Newtonian mechanics, space is absolute, and there is, in principle, a fact of the matter about whether an object is really moving or really at rest. Newton argued for this position on the basis of his famous bucket experiment, in which a rotating bucket of water develops a concave surface, demonstrating that the water knows it is rotating even in the absence of any external reference point. However, in the context of general relativity, the situation is more nuanced. General relativity replaces the concept of absolute space with the dynamical geometry of spacetime, and the distinction between real motion and apparent motion becomes dependent on the choice of coordinates, which are, in principle, arbitrary. The question of whether the Milky Way is really moving at 620 kilometers per second through space, or whether the CMB rest frame is really at rest, does not have a well-defined answer in general relativity. Both descriptions are equally valid, and the choice between them is a matter of convenience rather than physical truth. That said, there is a sense in which the CMB rest frame is physically distinguished. In the standard Friedmann-Lemaitre-Robertson-Walker cosmological model, the universe is homogeneous and isotropic on large scales, and the CMB rest frame is the frame in which this homogeneity and isotropy are manifest. An observer at rest relative to the CMB sees the universe expanding uniformly in all directions, with no preferred direction or axis. An observer moving relative to the CMB sees a dipole in the CMB temperature, breaking the apparent isotropy, and the universe appears to be expanding faster in some directions and slower in others, though this is entirely a consequence of the observer's motion, not of any real anisotropy in the expansion. In cosmological perturbation theory, the CMB rest frame is the natural frame for defining the perturbations in density, velocity, and gravitational potential that give rise to the large-scale structure of the universe, and it is the frame in which the physics of the early universe is most simply described. So while no frame is more real than any other in a fundamental sense, the CMB frame is the frame in which the cosmological model is most naturally and simply formulated, and it is in this sense that it serves as the closest thing we have to a universal rest frame. The question of cosmic velocity also intersects with the history of ether theories and the development of modern physics in ways that are worth exploring. Throughout the 19th century, it was widely believed that light waves, like sound waves, required a material medium for their propagation, and this hypothetical medium was called the luminiferous ether. If the ether existed, then the Earth's motion through it should be detectable by measuring differences in the speed of light in different directions. Since light traveling in the direction of the Earth's motion through the ether should appear to travel slightly slower, while light traveling perpendicular to the motion should be unaffected. The Michelson-Morley experiment of 1887, which used a precision interferometer to search for such differences, found no detectable effect, despite having sufficient sensitivity to measure the expected effect of the Earth's orbital velocity of 30 kilometers per second. This null result was deeply puzzling and resisted explanation within the framework of classical physics. Various attempts were made to account for the Michelson-Morley result within the ether framework. George Fitzgerald and Hendrik Lorentz independently proposed that objects moving through the ether contract in the direction of motion by a factor that exactly compensates for the expected time difference, a hypothesis known as length contraction. Lorentz further developed this idea into a comprehensive mathematical framework, the Lorentz transformations, which related the space and time coordinates of events in different inertial frames. However, in Lorentz's version of the theory, there was still a preferred frame, the ether rest frame, and the contractions and time dilations were real physical effects caused by motion through the ether. It was Einstein in 1905 who reinterpreted the Lorentz transformations as expressing a fundamental symmetry of nature, applying equally in all inertial frames, with no preferred frame and no ether. In Einstein's theory, the speed of light is the same in all inertial frames, not because of some conspiracy of physical effects that happen to cancel out the expected differences, but because the very concepts of space and time are frame-dependent in a way that ensures the constancy of the speed of light. The discovery of the CMB in 1965 might have seemed to resurrect the ether concept, since the CMB provides a frame that can be detected experimentally, much as the ether was supposed to. However, the crucial difference is that the CMB frame does not affect the laws of physics. An experiment performed in a laboratory moving at 620 kilometers per second relative to the CMB gives exactly the same results as one performed at rest relative to the CMB, provided the experiment does not involve detecting the CMB itself. This is fundamentally different from the ether, which was supposed to affect the speed of light and, through it, all electromagnetic phenomena. The CMB is a physical substance, a gas of photons filling the universe, and one can measure one's motion relative to it, just as one can measure one's motion relative to the air, the ocean, or any other physical medium. But unlike the ether, the CMB does not define a preferred frame for the laws of physics. This point connects to a broader theme in the history of physics: the gradual recognition that many concepts that seem fundamental and absolute, such as absolute space, absolute time, and absolute simultaneity, are in fact relative and frame-dependent. The motion of the Earth through space is a real physical phenomenon with measurable consequences, but the speed at which the Earth is moving depends entirely on what reference frame is chosen, and no choice of reference frame is privileged by the laws of physics. The answer to the question, how fast are we really moving through space, is therefore inherently ambiguous, and the word really in the question betrays an intuition about absolute motion that physics has shown to be unfounded. Let us now consider some of the more subtle and less commonly discussed aspects of cosmic motion. One is the question of whether the peculiar velocity of the local group relative to the CMB is changing over time. The gravitational attraction of the Great Attractor and other large-scale structures is continuously accelerating the local group, but the expansion of the universe is simultaneously carrying those structures away, reducing the gravitational force. The net effect depends on the density and distribution of matter in the local universe and on the rate of cosmic expansion. In a universe dominated by matter, the peculiar velocities would grow over time as gravitational instability amplifies density perturbations. In a universe dominated by dark energy, as ours appears to be at the present epoch, the expansion accelerates and the growth of peculiar velocities slows down. The transition between these two regimes occurred several billion years ago, when the density of dark energy began to exceed the density of matter, and since then, the growth of large-scale structure has been gradually suppressed. This means that the peculiar velocity of the local group is not expected to increase significantly in the future. In fact, as the universe continues to accelerate, the gravitational influence of distant structures will diminish, and the peculiar velocity may gradually decay, though this process would take many billions of years. Another interesting aspect is the direction of our cosmic motion. As mentioned, the Milky Way's velocity relative to the CMB is directed approximately toward the constellation Centaurus, but the precise direction and its uncertainty are important. The Planck satellite measured the CMB dipole direction as right ascension 11 hours 11 minutes, declination -6.9 degrees. In galactic coordinates, this corresponds to galactic longitude 264 degrees and galactic latitude 48 degrees. This direction is roughly between the constellations Leo and Crater, but this is the direction of the Sun's motion relative to the CMB, not the Milky Way's motion. When the Sun's galactic orbital velocity is subtracted, the resulting direction of the Milky Way's motion relative to the CMB shifts to approximately galactic longitude 276 degrees and galactic latitude 30 degrees, which is in the direction of the constellation Centaurus. The fact that multiple independent lines of evidence, the CMB dipole, galaxy peculiar velocity surveys, the distribution of galaxy clusters, and the identification of voids, all point toward a consistent picture of our cosmic motion, lends considerable confidence to the current understanding. However, there are still open questions. For instance, some studies have found that the direction and magnitude of the bulk flow of galaxies on very large scales, beyond several hundred megaparsecs, are larger than expected from the standard lambda CDM cosmological model. A 2008 study by Alexander Kashlinsky and collaborators, using data from the WMAP satellite and a catalogue of galaxy clusters, claimed to detect a coherent flow of clusters extending to distances of at least 800 megaparsecs, which they dubbed the dark flow. If confirmed, this would suggest the influence of structures or dynamics beyond the observable universe, potentially related to pre-inflationary conditions. However, the dark flow claim has been disputed by other groups, including the Planck collaboration, who found no significant evidence for such a flow in their data. The issue remains unresolved, and it is a good example of how pushing observational precision to its limits can lead to results that are at the boundary between signal and systematic error, where the interpretation depends sensitively on the methods used to analyze the data. The question of our velocity through space also has some unexpected connections to particle physics and high-energy astrophysics. The flux of cosmic rays, high-energy particles, from astrophysical sources that bombard the Earth's atmosphere is expected to be slightly anisotropic due to the Earth's motion through the cosmic ray background. This anisotropy has been detected by experiments such as IceCube and AAWC, though interpreting it is complicated by the fact that cosmic rays are deflected by magnetic fields in the galaxy and the heliosphere, making it difficult to trace them back to their sources. Similarly, the expected flux of certain dark matter candidates, such as weakly interacting massive particles, would depend on the Earth's velocity through the galactic dark matter halo. As the Earth orbits the Sun, its velocity relative to the dark matter halo changes, and this annual modulation in the expected dark matter signal has been the basis for several experimental searches, most notably the Dama R. Labra experiment in Italy, which has reported a positive detection of annual modulation for over 2 decades, though no other experiment has confirmed this result with the same type of detector technology, and the interpretation remains highly controversial. The measurement of high-precision velocities has also become important for gravitational wave astronomy. The LIGO and Virgo detectors, which detect gravitational waves from merging compact objects such as black holes and neutron stars, are sensitive to the phase and amplitude of the gravitational wave signal, both of which can be affected by the motion of the detector relative to the source. For routine detections, these effects are small and can be accounted for in the data analysis, but for very precise measurements, such as tests of general relativity or measurements of the Hubble constant using gravitational wave standard sirens, the motion of the Earth relative to the CMB, the galaxy, and the source must be carefully modeled. In the context of future space missions, the velocity of the solar system through the galaxy has practical implications for interstellar travel, should it ever become feasible. The nearest star system, Alpha Centauri, is approximately 4.37 light-years away, and at the Sun's galactic orbital velocity of 228 kilometers per second. The solar system is not heading directly toward Alpha Centauri. In fact, the relative velocity between the Sun and Alpha Centauri is only about 32 kilometers per second, and the direction of relative motion is such that the separation is currently decreasing very slowly. Any spacecraft attempting to reach Alpha Centauri would need to achieve a velocity relative to the Sun of a significant fraction of the speed of light, and the motion of the solar system through the galaxy is largely irrelevant for such a journey, since both the Sun and Alpha Centauri are moving through the galaxy together with only a relatively small differential velocity. However, for more ambitious scenarios, such as missions to other galaxies or to the far reaches of the Milky Way, the solar system's velocity through the galaxy becomes relevant. The direction of the Sun's galactic orbit means that a spacecraft launched in the direction of the Sun's motion would have a head start of 228 kilometers per second relative to the galactic center, while one launched in the opposite direction would need to overcome this velocity before making any progress. Of course, these considerations are purely theoretical at present, given that current propulsion technology can achieve exhaust velocities of only a few tens of kilometers per second at most, and even the most ambitious proposed technologies, such as laser sail propulsion of the kind envisioned by the Breakthrough Starshot initiative, would achieve velocities of at most about 60,000 kilometers per second, or about 20% of the speed of light for very small, lightweight probes. Let us now consider the philosophical and conceptual dimensions of the velocity question in more detail. The idea that motion is relative and that there is no meaningful sense in which one can be absolutely at rest or in absolute motion is one of the foundational principles of modern physics. It was articulated in various forms by Galileo, Newton, who nonetheless believed in absolute space, Leibniz, who rejected absolute space and argued that only relative motion was meaningful, and ultimately Einstein, whose theories of special and general relativity placed the relativity of motion on a rigorous mathematical footing. The question, how fast are we really moving through space, implicitly assumes that there is a single correct answer, but the physics tells us that the answer depends on the choice of reference frame, and all frames are equally valid. This does not mean, however, that the question is meaningless, or that all answers are equally useful. For different purposes, different reference frames are appropriate. For navigation on the Earth's surface, the relevant reference frame is the Earth itself, and speeds are measured relative to the ground. For orbital mechanics, the relevant frame is centered on the body being orbited, whether that is the Earth, the Sun, or another planet. For galactic dynamics, the relevant frame is the galactic center, or the local standard of rest. For cosmology, the relevant frame is the CMB rest frame. Each of these frames serves a specific purpose and reveals a specific aspect of the physical situation. The value of asking about our cosmic velocity is not that it reveals some hidden truth about our real state of motion, but that it illuminates the layered hierarchical nature of the gravitational systems in which we are embedded, from the rotation of the Earth to the expansion of the universe. The educational value of exploring these layers of motion is considerable. Each layer introduces new physics, new observational techniques, and new conceptual challenges. The rotation of the Earth introduces the concepts of angular velocity, centripetal acceleration, and the Coriolis effect. The orbit around the Sun introduces Kepler's laws, Newtonian gravity, and the concept of the gravitational potential. The Sun's motion within the galaxy introduces stellar dynamics, the concept of the rotation curve, and the evidence for dark matter. The motion of the Milky Way within the local group introduces the dynamics of galaxy interactions and the concept of the virial mass. The motion relative to the CMB introduces special relativity, the Doppler effect for electromagnetic radiation, and the concept of the cosmological rest frame. And the recession of distant galaxies introduces general relativity, the expansion of the universe, and the concept of the scale factor. Each layer builds on the ones below it, and together they provide a comprehensive tour of modern physics and astronomy. There is a final point worth making about the nature of these velocities, which concerns the question of acceleration. All of the motions described, the rotation of the Earth, its orbit around the Sun, the Sun's orbit around the galaxy, the infall of the local group toward the great attractor, are accelerated motions, involving continuous changes in the direction and sometimes the magnitude of velocity. These accelerations are, in every case, the result of gravitational forces, and by the equivalence principle of general relativity, a freely falling observer in a gravitational field experiences no force and detects no acceleration. The Earth is freely falling around the Sun is freely falling around the galaxy, and the galaxy is freely falling toward the great attractor. In each case, the apparent acceleration is a manifestation of the curvature of spacetime produced by the relevant mass distribution, and a sufficiently small, freely falling laboratory would detect no local effects of this acceleration. The only acceleration that is felt in a direct physical sense is the one due to the surface of the Earth pushing upward against us, counteracting the gravitational pull of the Earth and preventing us from freely falling toward its center. In a very real sense, the only acceleration most people experience in their daily lives is the 9.8 meters per second squared directed upward from the ground, which is what we perceive as gravity. This insight, that gravity is not a force in the usual sense, but rather a manifestation of the curvature of spacetime, and that the apparent effects of gravity can be made to vanish by choosing an appropriate, freely falling reference frame, is one of the most profound conceptual achievements of 20th century physics. It means that the question, how fast are we moving, is inextricably linked to the question, how is spacetime curved in our vicinity, and that any complete answer to the first question must take into account the second. To recapitulate the specific numbers without oversimplifying the picture, a person on the Earth's surface at the equator is moving at approximately 465 meters per second, relative to the Earth's axis due to rotation. The Earth is moving at approximately 29.8 kilometers per second, relative to the Sun in its orbit. The Sun is moving at approximately 228 kilometers per second, relative to the center of the Milky Way. The Milky Way is moving at approximately 620 kilometers per second, relative to the cosmic microwave background, which is the most universal and well-defined reference frame available in cosmology. The total speed of an observer on Earth, relative to the CMB, varies with time and location due to the changing alignment of the various velocity components, but it is typically in the range of 300 to 400 kilometers per second for the Sun, and the full vectorial combination of all components at any given instant yields a specific number that can, in principle, be calculated to arbitrary precision, given sufficient knowledge of the relevant orbital parameters. These numbers, large as they are not directly experienced by any human being, and this fundamental imperceptibility is itself one of the most important lessons of modern physics. The universe is not arranged for human perception. The scales of speed, distance, time, and energy that characterize cosmic processes are so far removed from everyday experience that they can only be apprehended through measurement, theory, and the patient accumulation of evidence over centuries. The fact that we can, nonetheless, determine our cosmic velocity to a precision of a few kilometers per second is a testament to the power of the scientific method and the remarkable instruments, from Michelson's interferometer to the Planck satellite, that have been developed to probe the universe at scales and sensitivities far beyond anything accessible to unaided human senses. The story of how we came to know our velocity through space is, in miniature, the story of how humanity learned to think about motion, space, time, and the structure of the universe. It encompasses contributions from dozens of scientific disciplines, thousands of individual researchers, and centuries of effort. Each measurement, each conceptual advance, and each technological innovation has added a new layer to our understanding, and each layer has revealed that the universe is larger, more complex, and more dynamic than previously imagined. The question, how fast are we really moving through space, has no single definitive answer, but the attempt to answer it has driven some of the most important discoveries in the history of science, and it continues to motivate new observations, new theories, and new ways of understanding our place in the cosmos. The various motions described in this account are not independent phenomena occurring in isolation from one another. They are deeply interconnected manifestations of the same set of physical laws operating on different scales. The gravitational force that holds the Earth in orbit around the Sun is the same force, described by the same equations, that holds the Sun in orbit around the galactic center, that draws the local group toward the great attractor, and that shaped the density fluctuations in the early universe that eventually grew into galaxies, clusters, and superclusters. The universality of gravity, the fact that it operates on all scales from the submillimeter to the cosmological, is one of the most remarkable features of the physical world, and it means that our cosmic velocity is ultimately a consequence of the same fundamental interaction that keeps our feet on the ground. The uniformity of the CMB to 1 part in 100,000 is both a testament to the homogeneity of the early universe and a constraint on theories of cosmic evolution. The tiny fluctuations in the CMB temperature correspond to slight variations in the density of matter about 380,000 years after the Big Bang, and these variations, amplified by billions of years of gravitational instability, produced the large-scale structures that are now pulling us through space at hundreds of kilometers per second. In this sense, our current velocity relative to the CMB is a direct relic of conditions in the very early universe, encoded in the pattern of density fluctuations that were imprinted during the epoch of cosmic inflation, a hypothetical period of exponential expansion in the first fraction of a second after the Big Bang. The statistical properties of these fluctuations, their amplitude, spectrum, and spatial distribution, are among the key predictions of inflationary models, and the observed peculiar velocities of galaxies, including our own, provide one of the many tests of these models. The hierarchical nature of cosmic structure, from planets to stars to galaxies to groups to clusters to superclusters to the cosmic web, is reflected in the hierarchy of velocities described in this account. At each level, the velocity relative to the center of mass of the next larger structure is determined by the balance between gravitational attraction and the orbital dynamics of the system. The rotation of the Earth is determined by the angular momentum acquired during its formation from the protoplanetary disk. The Earth's orbital velocity is determined by the mass of the Sun and the Earth's distance from it. The Sun's galactic orbital velocity is determined by the mass distribution of the Milky Way and the Sun's distance from the galactic center. The motion of the Milky Way within the local group is determined by the masses and positions of the other galaxies in the group, and the motion of the local group relative to the CMB is determined by the distribution of mass on scales of hundreds of millions of light-years, including both the overdensities that attract us and the underdensities that fail to attract us, producing an effective repulsion. This nested structure of motions is a direct consequence of the way gravitational instability works in an expanding universe. Small perturbations in density grow over time, but the growth rate depends on the scale of the perturbation and the background expansion rate. On small scales, perturbations grow quickly and collapse into bound structures early, producing stars and galaxies. On larger scales, perturbations grow more slowly and may not have had time to collapse by the present day, producing the filamentary structures and voids of the cosmic web. The peculiar velocities associated with these structures reflect the gravitational fields they produce, and since larger structures have larger gravitational fields but grow more slowly, the peculiar velocities at different scales form a consistent, if complex, picture that can be modeled and compared with observations. The measurement of cosmic velocities continues to improve with new observational programs and new technologies. The Gaia satellite, launched by the European Space Agency in 2013, is measuring the positions, distances, and proper motions of more than 1 billion stars in the Milky Way with unprecedented precision, providing detailed information about the kinematics and dynamics of the galaxy, including the rotation curve, the velocity dispersion, and the presence of substructure in the stellar populations. These data are already refining estimates of the Sun's galactic orbital velocity and the structure of the Milky Way, and they are expected to continue doing so as more data are released and analyzed. On cosmological scales, surveys such as the Dark Energy Spectroscopic Instrument, DSI, and the Vera C. Rubin Observatory's Legacy Survey of Space and Time, LSST, will measure the redshifts and distances of millions of galaxies, mapping the velocity field of the local universe with much greater detail and precision than currently available. These data will test the predictions of the Lambda CDM model, constrain the properties of dark energy, and potentially reveal new features of the cosmic velocity field that are not yet known. The journey from the simple observation that the Earth rotates to the modern measurement of our velocity relative to the cosmic microwave background spans more than 2 millennia of intellectual history, and it has involved contributions from virtually every branch of physical science. It is a story of gradually expanding horizons, both literal and conceptual, in which each new discovery revealed that the universe was larger, more dynamic, and more interconnected than previously imagined. The numbers themselves, 465 meters per second for the Earth's rotation, 29.8 kilometers per second for the Earth's orbit, 228 kilometers per second for the Sun's galactic orbit, and 620 kilometers per second for the Milky Way's motion relative to the CMB, are remarkable for their magnitude. But even more remarkable is the fact that we can measure them at all, using instruments of extraordinary precision and theoretical frameworks of extraordinary power. Every person alive right now, sitting in a chair, walking down a street, or lying in bed, is simultaneously rotating with the Earth, orbiting the Sun, circling the center of the Milky Way, falling toward the great attractor, and being carried along by the expansion of the universe. None of these motions are felt. None of them leave any trace in ordinary experience, and yet they are as real and as precisely measured as the speed of a car on a highway. The universe is not a static backdrop against which events unfold. It is itself in constant, violent motion, and we, embedded within it at multiple scales of gravitational structure, are swept along in a complex choreography of forces and accelerations that extends from the ground beneath our feet to the most distant reaches of the observable cosmos. The precise answer to how fast we are moving through space depends ultimately on what we mean by through space. And this seemingly simple question opens up the entire edifice of modern physics, from Galilean relativity to general relativity, from Newtonian gravity to dark energy, from the rotation of the Earth to the expansion of the universe. The richness of the answer is what makes the question worth asking, and the fact that the answer is not a single number, but a hierarchy of numbers, each defined relative to a different reference frame, and each revealing a different aspect of our physical situation, is itself one of the most profound insights that physics has to offer about the nature of motion and the structure of the cosmos.